Hello everyone, I hope you are doing well. So in today's video, we're going to go through the 2025 VCE Northern Hemisphere Maths Methods Exam 1. I heard a lot of students, who went through this paper said it was such an ugly paper. It was very hard. So I'm really fascinated because I really want to try it out. So this is my first time trying it. And let's see if it is true. I'll give my own rating, see how the paper is compared to the other years, of course. And yeah, and just like always, guys, if you guys want private tutoring in specialist methods, physics, or chemistry, you can always email me through this email. Now, guys, take this as a caution. These are my suggested solutions. If Vika hasn't posted solutions, they'll probably take 2 months until they actually post their solution. So for those who want to just, take my solutions as an example, take it. It's all up to you. Again, they are suggested solutions. And if you see any mistakes, let me know. Again, this is my first time trying it, and you will see, hopefully I don't make any mistakes, but I'll take my time. So in this paper, I will take my time, absolutely, because I want to make sure I go as much detail in explaining every little concept and how I kind of think critically. So a lot of students can see how to think and break down questions. That's what my goal is. I'm gonna try to break down every question. So it's probably gonna take longer than an hour. This paper is 1 hour, but what my goal is to explain how I break everything down and how my thinking works. So good luck, everyone. And I hope for those who are doing, and I just want to say, of course, congratulations to those students who have completed this paper, the exam 1 and 2. I hope it went well. I know it was a hard paper from what I heard from you guys. I will try it out and see, hopefully, if it's not too bad, yeah? Good luck. I mean, you are finished, basically. You're finished. Like, you finished those exams, so you can take a rest, you can sleep, you can, do whatever you want. And I hope these helps the November students, especially those who are doing their exams in November. Let's smash through this paper. Let's go. So we have question 1. Okay, so 4 marks. And we have a question rule. We got 2 functions being divided by each other. So find and simplify dy dx. What a beautiful question. So of course, this is quotient rule. So so this is here quotient. So we can say quotient rule. So this is a quotient rule question, and let's go through it. So this is a quotient rule. And how I break down quotient rule is this. So I always let u be the top function. Remember, your u is your top function. Your u here is your top function. And your v is your bottom function, yeah? So let's write those down. So, of course, my u is my top function, so it's log ex. And my v is my bottom function, which is x to the power of 3. And I'm going to derive u dash, so which is, remember, deriving log. If you don't know how to derive logs, a log, so for example, if you have a log and a function, like that, f of x, and you want to derive this here, so d dx this, yeah? Like that. If you want to derive this, it's basically just this. It's f dash of x over f of x. This is what the derivative is. Do you see that? So you derive what's inside the log. So f dash of x over f of x. For example, if I got log e x squared plus 1, remember, this is my f of x. So I derive, x squared plus 1, which is just 2x, over rewriting it, so f of x, so x squared plus 1. This is my derivative, and that's how you derive logs. So in our case, this one over here, this one here, it's log e of x. So our f of x is x, so deriving that is just, of course, 1 over the function f of x, which is x. Beautiful. And v dash is, deriving this one, is 3x squared. And remember, quotient rule, this is how you do it. It's v times u dash minus u times v dash. These two multiplied here. Yep. So again, v times u dash, so these two first, which is basically going to be, in this case, let me write dy dx here. So dy dx is equal to, let me put it here. So it'll be 1 over x, so times x to the power 3. So these two multiplied minus these two multiplied here, which is 3x squared log ex. Now, as you can see here, this is, when you simplify, it's basically x squared. Let me rub that out. It's x squared. And don't forget, to complete the quotient rule, don't forget the v squared at the bottom. So you know how this is your v? Imagine squaring it, yeah? Like squaring that, which is basically x to the power of 6. Now we can simplify this much further, because remember, they're telling us to simplify. So what we have to do is that you can see how there's a common factor of x squared on the top. So let's take that as a common factor. Okay. All over x to the power 6. And that, cancels out with that, and that'll be a power 4 here, which you can just simply take that out, and that is your final answer. So, okay, let's write this nicely now, like that. So put this over here, like that. Hence, your basically dy dx is this as a final answer. So 1 minus 3 log e, it's that. So let's highlight that. A really beautiful, nice question to start off the paper. So easy. Okay, next question. Let f of x be sine pi e3x, evaluate f dash of 0. A really beautiful question. So let's do this one too. So remember how to derive sine. What we have to first do is derive the inside. So pi e to the power of 3x. So to derive this, so let's think about it. So this is a constant. That pi is a constant. It's basically just put that pi outside, and we're basically just deriving e3x. Remember, to derive an exponential, we derive the top of it. So what's the derivative of 3x? It's 3. And we bring the 3 into the front, and we rewrite the whole exponential. So it's just basically 3 pi e3x. That's the derivative of the inside. So 3 pi, so let me write f dash of x, by the way. F dash of x will be 3 pi e3x. And then what we need to do is derive the sine, the outside. So the derivative of sine is cosine, and rewrite the whole thing. So pi e3x. Beautiful. This is the derivative of this. Of course, you can use chain rule. There's reason, this is called the fast chain rule. Do not use the long chain rule. It's because it's 2 marks. Like, all you're going to get a mark is to find the derivative and to substitute that 0 in. So that's 1 mark. And what we need to do then is sub in that 0. So f dash of 0 is 3 pi e, that'll be 0 on top here, cosine pi e0. And remember, e to the power of 0 is 1. So it's going to be 3 pi cosine pi, and we know that cosine pi is what? Again, if you don't know what who that is, just draw a basic cosine graph like that. Remember, that's 2 pi here, and pi is over here. Remember, that's 1, that's negative 1. As you can see, when it's pi cosine pi, what's our value? It's negative 1. So this one over here is 3 pi negative 1, which hence your f dash of 0 is negative 3 pi. That is your final answer. So not too bad. It's always, these questions always, every paper starts, so every VCAR paper starts with differentiation. Really easy, full marks you can get in these ones. Okay, question 2. Let G, where G has a domain of all reals, G of x be this cubic, where A, B, and C, we don't know what they are, but they're all real numbers. And H, which is all real, and it's a quadratic, as you can see, x squared over 4. The graph of G of x, so that cubic, passes through the point 0, 9. And as you can see, here it is. You got the dotted line, which is our cubic, our G of x, and you can see how the y value of it is 0, 9, it says. And the graph of G of x and H of x pass through this point 6, 9. So they basically intersect at that point. They have a common intercept together. This is their basically intersection, which is 6, 9. And they also have the same gradient at that point, meaning that the gradient of the tangent for both H of x and G of x is the same at x equals 2. And the graph of G of x and H of x are shown below. Beautiful. Find the values of A, B, and C. Not too bad. So first of all, for example, what are we finding? Well, we're finding 3 variables, A, B, and C. So we need to make 3 simultaneous equations. Well, the easiest case, of course, is writing the function g of x down first. So g of x is equal to a, what was it? A x to the power 3 plus bx squared plus c. Is that correct? Just double check. Yes, it is. So first of all, we know that can you see how your g of x, it passes through 0, 9. This is the y-intercept. So we can actually sub that in first. So what we can do is we first sub in, your first equation is basically sub in g of, so the x value is 0, and it should output, what comes out is 9, the y value. So dot dot, and let's actually do this. So that will mean that, so it'll be a, so you're summing all the x values 0. So 0 to the power 3 plus b, 0 squared plus c, and that all equals 9. Now that's 0, and you're just left out with c equals 9. Absolute beauty of a question. So we already find c equals 9. Nice. So already found one of those. How much free, is it 3 marks? Yeah, so that's already 1 mark there. Now to get the other ones, well, we have some other stuff. So for example, we have another thing. Well, we also know that g of x passes through the point 69. So what we can do is the same thing. So g of 6, when, x is 6, it's equal to the y value equal to 9. So, and we can do that too. So it'll be a 6 to the power of 3. Actually, let me write it in yellow. So it'll be all the same color. And 6 to the power of 3 plus b 6 squared. By the way, c, now you can actually put c as 9 here. So you just put 9 there. But yeah, now we know what it is. Plus 9, and that's all going to be equal to your 9 here. And guess what? The 9s actually cancel out because they're both 9 out. If you minus 9 on both sides, you actually cancel that out. So it'll be equal to 0. And guess what? You can actually see these 6's over here. You can actually take a common factor, yeah? Like 6 squared out of both of them. So it'll be like 6a plus b equals 0. And of course, dividing both sides by 6 squared, it's just 0. Those 6's just disappear. And this is beautiful. So your b value, in this case, your b value, if you rearrange it, is negative 6a. What a beauty. So that's already one thing that we can use to, it's like a simultaneous equation. We have 1 point. We need one more. Well, they also tell us, remember, that they have the same gradient at that point 69. What that means is, remember that the gradient of the tangent for both h of x and g of x at that point x equals 6 is going to be the same. So we can write this as this, by the way. So in algebraic terms, so in functional terms. So what we're saying is basically g dash, so the derivative at the point for g, of course, when you sub in the point 6, so this is going to give you the gradient of the tangent at point 6, is going to be the same as the gradient of, the gradient of h at that point 6. Beautiful. So what we need to first do, of course, is derive first what's d dash of x. And that's really easy because we got g of x here. Imagine deriving it. So you bring the 3 in front, ax squared plus 2bx plus 9. Beautiful. So this is, so my apologies, that 9 disappears. It's a constant, remember? When you derive that disappears. So yep, just double checking if I've not made any mistakes, any simple, okay, beautiful. And so, yep, so that's that. And imagine subbing in 6 in there. 3a 6 squared plus 2b6. Now I'm going to leave it as what it is. I'm not going to simplify. You can simplify, but I just leave it because I'm going to try to do the other one now. So the other one is basically h dash of x. It's now deriving h dash. So of course, h of x is what? It's this here. It's beautiful. So remember, it's just the power rule. You bring the 2 in front out of that 1 over 4, and it'll be x. So it'll be basically x over 2 as your derivative. So x over 2. Rub that out. All right, so it'll be x over 2, and of course, subbing h dash of 6 will be 3. The derivative equals 3. And remember, putting now into this equation where 3a 6 squared plus 2b6 has to be equal to 3. And guess what? I mean, you can see quite a lot happening here. Like, for example, you can divide all this equation by 3. Yeah, like if I divide this by 3, I can divide all of this by 3. Like, we know how many 3s going to this first part here. This 3 will cancel out if I divide it. If I divide this part by 3, this will 6 will be 2. And if I divide this by 3, it'll be 1. Does that make sense, everyone? So I divided everything by 3, and that's nice. So, and I'll expand it. So like 6 squared is 36a plus 4b equals 1. Beautiful. And now, guess what? We can sub in this statement over here to find b and a by using substitution. So 36a plus 4, our b value, by the way, is negative 6a, equals 1. So coming here, so, continuing here, so it'll be 36a, 6, 12, 18, 24, so minus 24a equals 1. So 36a minus 24a is 12a equals 1. Hence our a value is 1 over 12. So we got our a value. Beautiful. Now to get our b value, it's really easy. So let me highlight that. To get our b value, it's really easy. Just sub that a value right into this equation over here. So let's do that. Use a different color. So b is equal to negative 6. And now what's our a value? 1 over 12, which is equal to negative 1 over 2. So let's write all of our answers here to summarize them basically. So a value is 1 over 12. So 1 over 12. Our b value is negative 1 over 2. And our c value is 9. Is that correct? C equals 9. 1 over 12 and b equals negative half. Beautiful. That's how you would work through this question. Not a bad question. It's kind of typical, this type of question. So not really bad right now. All these questions are really typical. So beautiful. Beautiful. Okay. Next question. Question 3. Let's do this one. So let f be, we don't know what the domain is, but f of x is this, where d is the maximal domain. Okay, find a general solution where f of x equals 0. Beautiful. So this here is, of course, going to be a general solution because it's a trig function. So let's let f of x be 0. So it'll be half tan x plus half equals 0. I'm going to minus the half on both sides. And I'm going to divide both sides by half, which is equal to negative 1. Now, when is tan negative? Draw a cast diagram. We know that it's negative, so we have, so like C, where its cosine is here, and A, S, and here. That's where sine is positive, so but tan is always negative at these two here. So in that quadrant and in that quadrant. Now, what's our base angle? Our base angle in this case is pi over 4. Remember? Pi over 4. Okay, and if you're wondering how to get the base angle, remember you can draw kind of, I like to always draw these right angle triangles, so like to find my exact value. So like, for example, if I have this over here, and imagine this here is the value of x. You know this like tan x, it's basically like negative 1 divided by 1 basically, where tan is of course opposite, so the opposite's 1 and the adjacent is 1. So the opposite's 1, the adjacent's 1, and remember this is root 2, and this angle has to be pi over 4. Remember that. So that's how we know our base angle, if you're wondering where we get the base angle. It's pi over 4. Beautiful. Now, we need to think of a general solution. So a general solution is like a solution that gives us infinite solutions of these over here. These solutions here. Now, remember, it's really easy. Have a look at this. For example, what you want to do for tan, if you haven't memorized them, is that, say we start here at 0, yeah? We start at 0, and if you minus pi over 4, remember, if you minus pi over 4, you reach this solution here. Yep, so, okay. If you plus pi, you'll be here, but if you minus pi over 4 again, it'll be this solution here. Basically, your general solution, if you don't know the general solution for tan, it's basically this. It's pi n. Pi n basically is where, for example, if n's an integer, so for example, n equals 0, you start here. If it's n equals 1, you start here. If n equals 2, you start again here. So it's always these points. It alternates between those 2 points, yeah? And what you want to do, if you alternate between 2 points, to get this solution, don't we minus pi over 4? So if we minus pi over 4, we get this one. So we're in here, we minus pi over 4, we get this solution. And this give us this infinite solutions, like this infinite loop of solutions. So if we minus that base angle pi over 4. Easy. So for example, let's try it. So for example, if I let n equals 0, this part would mean this part's 0, so you start over here. And you're minusing pi over 4, so you get this solution here. For example, if I sub in 1, so if I sub in 1 here, it'll be pi, so you start off here, and you're going to minus pi over 4, so it'll be here. And then look how beautiful it gives us all those infinite many solutions. Beautiful. And of course, what I would like to do, of course, is simplify this much further. So make it 4 pi n minus pi over 4. And your final answer, this is a really easy general solution. Tan's really easy, by the way. So you could take pi as a common factor, so it's 4n minus 1 over 4, and don't forget to state that n, because we've just introduced a new variable, n is basically like integers. So beautiful. That is nice. This is a really nice 2-marker here. Nothing too bad, so typical. Okay. Beautiful. Next question. Let g be where the functions or reals have this function. So g of x is sine 1 over d. Find all values of x such that f of x and g of x are equated together. Now, what happens? When you're equating two functions, you're actually finding the point of intersection between these two. And we want to find the point of intersection basically from negative pi to pi. A beautiful, typical question. Really nice question. So what we're going to do here is we're going to basically equate them. So f of x and g of x, yeah? So f of x is 1 over 2 tan x plus half, and that's going to be equal to g of x, which is this here, sine x plus half. And you can see how there's half on both sides. So if you minus half on both sides, these halves will cancel out. So we can actually just get rid of this halves nicely. Okay, now we know tan is basically sine over cos, yeah? So we can say this. Like tan is basically sine. We can replace that with sine over cos. What that equals sine x. Now these are multiplying basically, like these two are multiplying. So we can write that as like sine x over 2 cos x. You see, because sine, so like sine x times 1 is that, and 2 times that is that. So I'm going to rub this part out, so simplify it. But basically replacing it with this over here. Okay, now I'm going to make it as a common, like, not common factor, but like, I want to find it, like, make it a common denominator. So if you know how this is your denominator, so for example, I'm going to multiply both sides by 2 cos x. So if I multiply this by 2 cos x, it'll be just sine x. And then if I multiply this here by 2 cos x, it will be basically 2 sine x cosine x. Or in other words, what I'm saying is basically just multiply that by there. To make it like a linear. Not like you don't want it to have that fraction there, yeah? So can you see how I just multiplied that by there? That is it. And we have a nice equation here. And then what I'm going to do is we got both sides sine. I'm going to bring this to the other side. So it'll be 2 sine x cosine x minus that sine x. And now I have a common factor, yeah? So I can take sine x out, 2 cos x minus 1 equals 0. And you can actually now use the null factor theorem because you got two products being, like these two products here being equal to 0. So basically we have two types of, so when you solve it, you make this equal to 0 and you make this equal to 0. Let's do that there. So here, sine x equals 0, and then 2 cosine x minus 1 equals 0. Beautiful. Now, let's solve sine x equals 0 from, of course, this domain, negative pi to pi. Now, it's really easy by just graphing it, yeah? So let's graph it. Imagine you had a graph over here of a normal, just a sine graph. So actually from negative pi to pi, yeah? So let's draw a sine, one period of a sine. So imagine sine starts like that. You have this, and this is one period, remember? So that's 2 pi. Yep. And imagine drawing another one here, like that, and like that. A bit like that. So imagine that's negative 2 pi. We're drawing it from negative pi to pi. So pi is basically halfway here. So it's these points here. So for example, and it has to be an open circle, like that, open circles. And this also is an open circle. That's where the pi's are. And so I can rub that out and draw them a little bit nicer like that. And I'll rub this out and draw this nicer. So look, that's pi. And that's negative pi. Easy? That's it. So basically what we're saying is, hey, when is sine x, this red graph, equal to 0? So we know it's equal to 0 at only x equals 0. Because the other ones are not included. The pi and negative pi. Those are also solutions. But because remember, we're not including them. They're not within our domain. So our only solution is x equals 0. So this here will give us only x equals 0 as our answer. The next one is we have to solve it too. So basically bring the 1 to the other side and divide both sides by 2. We get cos x equals half. Beautiful. And it's how we normally solve our trigonometric equation. So, for example, we know that cos here is positive. So we draw a cast diagram where, here and here, these are your two quadrants where cosine is positive. And our base angle in this case is, of course, pi over 3. Here is pi over 3. And remember, you're going from the domain negative pi to pi. So this is your negative pi. And you're going all the way to pi, you get one solution. So that's 0. You get one solution, which is basically like 0 minus. So it'll be 0 minus pi over 3, your base angle. And the next one is, how you're starting at 0 plus 0 plus pi over 3. And that's it. Because, you're not going to go above that domain. So you get x equals negative pi over 3 and pi over 3. So our overall solutions, let's write them all nicely together now. So it will be, so x equals negative pi over 3, 0, and pi over 3. Nice. So we can actually highlight that. Beautiful. Not too bad. Next question, the graph of g of x is shown, okay? On the set of axes below, sketch the graph of f of x over this interval, negative pi over 2 to pi over 2, labeling all points where f of x and g of x basically intersect, because they're equating, with their coordinates and all asymptotes with their equation. Okay, so f of x is, what we're graphing is f of x, which is our tan graph. Of course, the tan graph has asymptotes. Now, let's think about them. I will just draw a rough sketch of a tan graph. So I'm going to draw as just like first 1 over tan x, just a 1 over tan x, not that translation up half units, just to see what it looks like. So for example, remember how to draw a tan. What I like to do is, for example, find the period. To find the period for a tan, it's pi over n, where n is the like a constant in front of the x, which is just 1 in this case. So the period is pi. So imagine this is pi. Let's call this pi. And what I do is I halve that pi. I halve it, it'll be an asymptote halfway through it. So this here is pi over 2. So there will be asymptote pi over 2. And so also here at negative pi over 2. And we'll have this graph. Look, we'll start at 0, and it'll be like that, or like that. And of course, we're only sketching it from negative pi over 2 to pi over 2, from what that domain is, you remember? So look, from that. So, and then if you're translating it like, you know, for example, you know, half units up. So if you put that half units up, it will just, you know, go up by half units. So like this will go up like half. So we'll go a half like that. I'm supposed to take that too, but like that's also good. But look, it'll go like half units up. But the asymptotes are still the same. So luckily, yeah, we know that there's going to be asymptotes at negative pi over 2 and pi over 2. Let's label those first. Let's go down here. Let's use a red color. Let's label those first. Show these dotted lines here. Okay, that's x equals pi over 2. What I'm going to do is I'm just going to kind of copy this here, duplicate it, right there, put it over here. That's my asymptotes at negative pi over 2. Beautiful. And so, yeah, this is what's happening. And now, what we're going to also do is, so for example, we know that the, like for example, the x value, this here is half, like this y value is a half, like 0, half, because you've basically, for example, if you sub in tan 0, it'll be 0, but you have the half here, so it'll be half. Because normally the original tan starts here, but you're translating half units up, so it's going to be actually over here. So let me choose a different color, like this color here. So it's going to be here. Actually, let's think about it. It's generally easy because we also know it's going to intersect. Remember, you're basically solving for f of x and g of x. We already know where they intersect. It's at 0, so here, and you see how it's intersecting it. And also it was intersecting it at pi over 3 and negative pi. Now, for example, this is nicely scaled because this these go by pi over 6. So that's pi over 6, that's pi over 3, and that's pi over 2. Beautiful. So pi over 3 is here. Yep, so that's pi over 3. And remember, there was a point of intersection, so it's going to intersect that graph of g of x. And also at negative pi over 3 too. So this is negative pi over 3. So we'll intersect it over here. Beautiful. So these are just a 3 point of intersection. One here, and one here. Beautiful. Now we can actually start a little bit breaking it more apart. So let's write the original function. So f of x is basically half tan x plus half. For example, midway through these, like midway is pi over 4, because we got pi over 2 here. Halfway through those, here is pi over 4, of course. If I sub in pi over 4 into this, so tan pi over 4 is 1, so it'll be half plus half, which is 1. So this here, if you sub in, it'll be over here. The y value when you sub in like this is pi over 4 here. The y value is 1. Beautiful. What about, for example, when you sub in, like, for example, negative pi over 4. Like, you know, negative pi over 4 is here. If I sub in negative pi over 4, it'll be negative half plus half, which is actually 0. So actually, it's an x-intercept here. Beautiful. And I've kind of actually, I can already see the graph, how it looks, of course. You remember, the graph's going to look like this. It must pass nicely through these points here. Oh, that looks so ugly, but let me make it nicer like that. Why is it? Come on. What is this rubbish? Come on. It's not gonna. Oh my god. No, I'm actually getting cut. What's happening here? Okay, let me a little bit bend it like that. If I can push it like that. Beauty. There it is. So look, passing through those points. So this is gonna look like that. This one is here. It's gonna look like this. It has to pass like that. Okay, I think if I a little bit bend it more and then I play around with it, so like this. Okay. Okay, now this is actually taking a piss out of me. Like I'm actually. There it is. Okay, what about if I push it like there, push it like there, push it like there, push it a little bit like there. Let me bend it more. There it is. Oh, that's a beauty. There it is. Okay, that's it. So this, look, that's tan graph, and it passes all those points nicely. And guess what? We just have to also, we've labeled the asymptotes. We just need to label all the points of intersection. That's easy because we've kind of calculated those, didn't we? So for example, this here is, of course, just by looking at it, it's 0 and it's half. This one over here is going to be like pi over 3, but what is the y value? Let's sub it into this equation over here. For example, like it'll be half. So tan pi over 3 is basically just root 3 plus half, so which is basically like root 3 plus 1 over 2. So it'll be root 3 plus 1 over 2. Yep, so is that correct? Is my right? Root 3 plus 1 over 2? Yep, that looks right. So the same with the other one. So the other one's like here, you're subbing negative pi over 3. The y value is, of course, going to be like, you know, subbing in. So, but tan, when you have a negative angle, you can just take that out. So it'll be tan pi over 3. Okay, plus half, which is negative root 3 over 2 plus half, which is basically 1 minus root 3 over 2, like that, which looks correct. So we've labeled all the point of intersection. Yeah, I mean, that's it. That's what they're asking us. So nothing more, nothing less. Don't put anything extra. Let's move on to the next question. Not too bad. Okay. Question 4. I can't even say that. Orchard contains a large number of apples. 1/3 of the apples are bruised. In a random sample of 4 apples, we have 4 samples. Find the probability that exactly 3 of those are bruised. What a beautiful, this is a binomial distribution. So what we're going to say is let X be binomially distributed. How many samples we have? We have 4 samples, and the probability that they are bruised of success is 1/3, so 1 over 3. And what we're trying to find the probability that exactly 3 are bruised. So when X equals 3, which of course just use your combinations formula. So which is, you know, 4 choose. So for the total number is 4. Choose 3. So the 3 here. Probability of success, which is 1 over 3. To the power of 3 here. Probability of unsuccess, which is 2 over 3. To the power of 4 minus 3, which is 1. Now, what's 4 choose 3? I like to use something called the Pascal's triangle. It just helps out a lot. Let's draw a Pascal's triangle here. So Pascal's triangle looks like this. You draw 1, you draw 1, 1. So these two add up, like 1, 1 add up. So that's going to be 2, yeah? And then, so for example, like these two add up, that'll be 2. And then you're left that 1, 1 here. So these two add up now. What's 1 plus 2? It'll be 3. These two also add up, that'll be 3. 1, 1. Can you tell it's just expanding? These two add up, that'll be 4. These two add up, that'll be 6. These two add up will be 4. 1, 1. You see how cool that is? Now, why do I use this? Because it's going to help out a lot. This basically tells me that to go 4 units down, and I've done that, so now we've reached the 4s, and means go 3 units to the right. So, of course, by the way, you start off 0, yeah? For example, that's 0, 1, 2, 3. See, that's 3 here. So the actual 4 choose 3 is 4. 4, that's your answer. So we can kind of replace that here with 4. We can write 4 there. That is what it simplifies to, and let's keep simplifying this. So that's going to be what? 4. 1 to the power of 3 is just 1. 3 to the power of 3 is 27. 2 over 3, which is 8 over, so 27 times 3 is 81. So basically 8 over 81. That is your answer for this one. Nice. So, yep, that looks quite good. So, next question. Let p hat be the random variable representing the proportion of bruised apples in a random sample of 10 apples from the orchard. So now our sample size is 10. So find the probability that p hat is less or equal to 1 over 10. Give your answer in this form where m and n are positive integers. Not too bad. This is actually quite similar to the 2024 Northern Hemisphere that was last year. So let's do it. First of all, what I always like to do is this is, of course, x is binomially distributed. So let x be like the number of bruised apples, and we have 10, yeah? Our sample's 10. And of course, the probability of a bruised is still 1 over 3. Now here, look at this. Now we're dealing with p hat. No one likes p hat. Convert it into x, yeah? So for example, To do that is we know that P, sorry, let me write that nicely. So we know that P hat is just x over n. Isn't that right? So our P hat in this case is 1 over 10. So we can write 1 over 10 here. Is equal to x over n. You remember n is the number of sample size, which is 10 in this case. So what's our x? Our x is equal to 1. Yeah? So we can actually rewrite this now in terms of x. The probability that P hat now is going to be x is less or equal to 1. Yeah? Look how nice. This is so much easier. And this here is equal to what? So probably that x is, less or equal to 1 is the probability that x equals 0 and 1. Yeah? So x equals 0 plus the probability of x equals 1. Beautiful. And so, of course, we have to use combination. Now we have two types, so we have to, because we have two parts we have to add. So I'm going to break them apart. So let's first find the probability that x equals 0. So it's going to, of course, it's going to be 10 choose. So remember the total. So your sample. So 10 choose 0. Probability of success, which is 1/3, to the power of 0. So this is 0 here. Probability of unsuccess, 10 minus 0, which is basically just 10. And remember, 10 choose 0 is 1. Anything to the power of 0 is 1. So these actually just all cancel out nicely. And that is actually 2 over 3 to the power of 10. Beautiful. Let's do that with, probably that x equals 1. Again, same thing. So it's going to be 10 choose, in this case, 1. So we have that. Probability of success. So 1 over 3 to the power of 1. Probability of unsuccess to the power of... So 10 minus 1, so you do have 10 minus 1, which is 9. Beautiful. And by the way, 10 choose 1 is just 10. And it makes sense. Like, for example, if you go back to this, yeah? For example, this here, if I was like, hey, what's 2 choose 1? Anything to the choose 1 here at the 1. So for example, 2 is here, yeah? You know how this is 0, 1. So when we reach 1, it's the same number as 2, yeah? The top power. Like, for example, what about 3? 3 choose 1. So you look at the 3 part. It means you go to, so you know how that's 0 and 1. Look, when you reach 1, it's 3. It's always the same number here, if you don't look at the pattern, yeah? So you realize, you're like, oh, okay, in this case, it's just 10. It is 10. Absolutely 10. Okay, which you can write basically 10 over 3. 10 over 3, because these multiply and put those together. And you can actually simplify that because, you can write this as, 10 here. Put times, you know how that expand this, so 2 to the power 9 over 3 over multiplied by 3 to the power 9. And can you see how that's 3 to the power 1? What happens if you have two of the same bases and then be multiplied? Their powers add up. So we can actually write these as 3 to the power of 10. And that 10 can also be simplified much further. You can write it as 5 times 2, yeah? Times, don't forget, 2 to the power 9. Yep, and guess what? Again, same base being multiplied is the powers add up. So it'll be to the power 10. And so you can see the pattern here. So we can now write this as nicely, leave the 5 outside. And so it's 2 over 3 to the power of 10. Because you remember, both have to the power of 10. So we can write them inclusively together. And that is beautiful because that actually looks the same as that. Look, to the power 10 to the power 10. And remember what our overall goal is? To add them up to find the probability that x is less or equal to 1. So overall, probability that x equals less than 1 is adding those up. So it'll be 2 over 3 to the power of 10 plus 5, 2 over 3 to the power of 10. So adding those up will be 6, 2 over 3 to the power of 10. And of course, we can still simplify that because remember, we want it in this. There's no 6 in front of it. We need to get rid of that 6. And it's easy to get rid of that 6 because we can write it as 3 times 2. 6 here. You can write it as 3 times 2. And then we got, expand this all. It'll be 2 to the power of 10 on top. And at the bottom will be 3 to the power of 10. And as you can see, these 3's cancel out. It'll cancel out one of the 3's here. So this 3 will cancel out. This will be to the power 9. And these 2, because you're multiplying with the same base, they'll add up. It'll be 2 to the power of 11. There it is. That looks like your final answer. What a beauty. So you can write that nicely now. Probably that x is less or equal to 1. It's 2 to the power 11 over 3 to the power of 9. Not too bad. So getting a little bit uglier, but it's still normal. Like this is what you would kind of expect from VCAR to put. So let's move on to the next question. Question 5. So we have f of x with a domain of all reals, which is this, and g of x, which also has, all reals. Is that? Find the x value of the point of intersection of the graph of fx and g of x. And remember, how do you find a point of intersection? You equate them. Yeah? So going back, we equate f of x with g of x. There it is. So basically e to the 2x equals ex plus 2. Beautiful. So move the other parts, all of these here, to this side, because you can kind of see the pattern. I think you guys see the pattern, do you? It's a quadratic. If you don't see it, for example, you can write this e to the power, 2x. You can write it as ex squared minus ex minus 2 equals 0. So if I let u be e to the power of x, I can replace this here. It will be u squared minus u minus 2 equals 0. And this is a beautiful quadratic. So nice. So 2 u's that multiplied, it gives you u squared. Two things that to multiply -2 is like -2. And if I put a 1 here, so it'll be 1 minus 2. That'll be negative. Beautiful. So this actually factorizes. So you can factorize this quadratic to u minus 2, u plus 1 equals 0. And solving that, now factor u equals 2 and u equals -1. And remember, this is not your solutions. You need to come back. Remember, u is e to the power of x. So replacing those u's, so e to the power of x equals 2 and e to the power of x equals -1. Aha, wrong. Be careful. E to the power of x equals -1. There's a problem with this. We know that exponentials are greater than 0, yeah? Remember that. Any exponential is going to be greater than 0. How the hell do we have -1 here? There's no solution. This actually doesn't exist. So we have to cross that, yeah? Does that make sense, everyone? So you cannot have an exponential having like equal to -1. It's always like greater than 0, yeah? Does that make sense? Like, so for example, if those who are just confused, it's like, think about it like this. You know how a normal exponential, when you graph it, looks like this. So you draw an exponential, it looks like this. Yep. And then y equals, like this -1 is here. Is there any point of intersection between these two? Because if there's any point of intersection, we get solutions. Now, there isn't, because remember, there's an asymptote here at y equals 0. It never even touches it. There it is. So be careful, guys. Remember, exponentials have to be greater than 0. Not even 0, because that's where the asymptote is, yeah? Be careful. So the only possible solution is this one over here. Look, it's a positive number. So it'll be, changing it into a log. So log e2 equals x. Hence, that is your answer. So log, basically like log e2x. That's it. Nice. So that's a nice 2 marker. Beautiful. Find the value of x. So value, so there's only one, of course, with the graph of f of x and g of x minus 1. So now g of x is translated 1 unit, right? Have equal gradients. This is a really nice question. So basically what you want to do here is, if you want equal gradients, you just want to derive both of them and equate them to each other, meaning that the gradient's going to be equal. And it'll give you where the x values for where the gradient is going to be equal. So what I'm going to do first is gx minus 1, which is, I'm going to find what the function is. So we know that, for example, x minus 1 is basically, what's your g of x originally? It's that. So basically all you're doing is summing for the x minus 1. So it'll be ex minus 1 plus 2. That's what basically gx minus 1 is. It's really simple. And of course our f of x is your e to x. Remember what we said? What we needed to find the equal gradients, we need to derive both of them. So g dash of x minus 1, you need to derive this function here and equate it with deriving f dash. So both of these gradients are going to be equal, and it's going to give you the x value. So let's do that. So to derive any exponential, remember, this is a constant, so that just becomes 0. How do you derive this? Remember, you derive the top. So what's the derivative of x minus 1? It's just 1. You bring it to the front and you rewrite it. So it'll be basically e to the power of x minus 1. E to the power of x minus 1. It's going to be equal to deriving f dash of x. Remember, you derive the top, which is just 2. Bring it to the front and rewrite it. So it'll be 2 e to x. Beauty. Now, to solve this, for example, we can actually split this up. So we can split it up to ex times e to the -1, because remember, same base, when they're being multiplied, their powers add up, and it's the same as this result over here. Okay, so 2e to x. And what I'm going to do is, I'm going to bring this to the other side. So it'll be 2e to x minus ex times e to the -1 equals 0. And you can, like, for example, like, this e to x, we can rewrite it as like ex times ex, yeah? because you remember 2 of the same bases, when add up, it'll be 2x, yep, minus ex times e to the negative 1 equals 0. And you can see that there's a common factor of ex. So taking ex out, it will be 2ex, basically minus e to the negative 1 equals 0. Am I correct? Let me just double check, seeing if there's any mistakes. 2e2x. Yep, that looks perfect. So remember null factor theorem now, yeah? Two products being multiplied. So this is going to be equal to 0, and this is going to be equal to 0. So that's going to be equal to 0, so ex equals 0. And 2ex minus e negative 1 equals 0. Aha, problem. E to the power of x equals 0. Remember what we said. E to the power, any exponential is going to be greater than 0, not equal to 0, yeah? Greater than 0. There's no solution for this one. We can cross that out. And so we're just looking at this one over here. So let's solve this one. 2ex. Bring that, so to the other side like that. Let's a little bit simplify it. We can write it as 1 over e, by the way. And multiply both sides by half to get rid of that 2. It'll be 1 over 2e. And then, of course, make it into a log. So log base e, 1 over 2e equals e to the, what am I doing? Equals x. Now, you can really write this nicely. This is so ugly. We can write this, you can write 2e to the negative 1, like that, equals x. And we can bring that negative 1 in the front. So your x can be basically negative log e 2e. That looks so much nicer compared to the other one. So that looks 10 times better. Beautiful. Done with that question. Okay, not too bad. Next question, question 6. A high jumper has up to 3 attempts to jump over a bar at a specific height. So once one attempt is successful, the higher jump does not make another attempt at this height. Okay, makes sense. At this height, let A be the event that the higher jump, so that the high jumper's first attempt is successful. Let B the event that the high jumper's second attempt is successful. Let C be the event that the high jumper's third attempt is successful. Okay, so the probability of A equals 0.6. That's what basically the probability that his first attempt is successful is 0.6. And the probability that B given A dash is equal to 0.5. Let N be a discrete random variable representing the number of attempts the high jumper makes at this height. Complete the table below for the probability distribution N. So first of all, let's absolutely understand what's happening here. There's a lot of information. So what I'm going to do is to think of it like this. So I like to draw a tree diagram in this case because there's actually a lot of information. So for example, if I draw a nice tree diagram like this, if I just break this apart, so a nice tree diagram. So let's say this first branch here is his first try, yeah? A, basically. This here, let's call it A. This branch here, sorry, let me write it in a different color. This first branch is A, yeah? Let's say this first branch is A. And of course, we have something, we have success here, and this is unsuccess. Success means like he basically makes it to A, like he jumps in his first try, he makes it over that jump, and he's successful, so that's S. And if this is when he's unsuccessful. Now, remember what they said. If he's successful, he stops. He's done. That's his height. Done. That's that. But if he's unsuccessful, he moves on to another try. He does another try, and that's your second try now. So basically what I'm going to do is I'm going to actually, let me move this up here. I'm going to copy this branch here, and this branch goes towards, so if he fails the first try, which is A, he gets the second try. When this phase is now called B. This phase is called B, and it has the same thing. So it has success and non-success. And of course, if he makes it to success, if he successfully makes it in B, basically where it's his second try, he stops. But if he doesn't make it, he has a third try, which is your now known as C. That's your third try. That's our C phase. And of course, there's S and S dash. So if he makes it successfully into C, like his third try, he actually successfully does it, that's perfect. He stops. Even if he is unsuccessful, he has to stop. He only has 3 tries, by the way. Does that make sense? So that's where it ends. And we've kind of nicely drawn a nice tree diagram to kind of represent this whole scenario nicely. Yeah? Now, let's see what's happening here. So the probability of A, basically remember what the probability of A is? A is the event that the high jumper first attempt is successful. He is successful in actually jumping that high. So come in here. So, well, there's only one phase that he's successful. It's just this. Jumper A, you know how this is his A phase? Like this is his A, that's your B, and that's your C. Well, remember when is he successful? There's only one part. It's his first try. He has to be 100% successful in his first try. And this here is, it's just basically this. The probability of A is just that, which in this case is, they told you probably A is 0.6. So we can actually just say, yeah, this is this here part is 0.6. Of course, this has to be 0.4 because remember, they have to add up to 1. Okay, perfect. And the next question says, hey, if you're wondering, this is conditional probability. Let's think about it. It said that given A, so he didn't, given A dash, remember A is the probability that he makes it into the first try, A, yeah? So they're saying basically, given that he did not make it in the first try, because A dash means did not make it in the first try. So given that he didn't make it in the first try, he made it in the second try. Remember, B is the second try. So basically, let's think what's happening here. What they're saying is, hey, he failed here. So in S, yeah, you know how that's, remember, this is your A, that's your first trial. He failed in S, like he basically failed, but then he actually successfully made it in the second try. So it's this part here. So it's actually this probability. So that probability, that conditional probability gives you this probability over here. And what is it? It is 0.5. So we can actually put 0.5 here. Does that make sense, everyone? So, yep. So for example, he fails. Of course, he has to fail A. Remember, he has to fail A to get into the second try. Yep. So if they said, hey, he's failed A, but he succeeds in B. Because look, given that he failed in A, he succeeds in B is 0.5, which is that little part there. Beautiful. So of course, this part here, of course, has to be also 0.5 because it has to add up to 1. Okay, beautiful. So let n be a discrete random variable, represent the number of, okay, complete this distribution. Okay, so we know that the probability of 1, basically this means he makes it in the first try, which is your A, yeah? Now, of course, in the first try, it's just 1, which is just, this here. This is that 0.6, that's why. What's the probability that he successfully makes it into 2? Well, it's easy. He first has to fail the first trial, which is A, and then he successfully has to make it into B. His second trial, he has to successfully make it. So it's basically 0.4, as you can see, it's just 0.4 times 0.5. Absolute beauty, which of course, damn, like it's 0.4 is just 4 over 10, I would write it. And 5 over 10 is basically, so that's like 2 over 5 times 1 over 2. These cancel out, it's just 1 over 5. 1 over 5 is basically 0.2. And so that's where we get that probability. So this here, the probability that he makes it successfully, in that, it basically he makes it successfully into 2, like the second trial is 0.2. And of course, this also has to be 0.2 because remember, adding all these have to be equal to 1. Beautiful. Find the expected n, the mean number of attempts that the high jumper makes at this height. What a beautiful question. To find the expected value, so to find the expected value, so expected value of n, remember it's very easy. You multiply n with with their own probability. So what's like 1 times 0.6 plus 2 times 0.2 plus 3 times 0.2, like that. So it'll be 1 times, I'm going to make them to fractions because I don't like decimals. So 6 over 10 is 0.6 plus 2 times 2 over 10 plus 3 times 2 over 10. Okay, so that's 6 over 10. Plus 4 over 10 plus 6 over 10, which is 16 over 10, which is basically 0.6. That looks easy. So 0.6, you can say. What am I saying? 0.6? It's 1.6. My apologies. Because 10 to go, yeah, 1.6. Or you can just simplify it into a fraction if you want. So it's 1.6, or you can say, so if you half 16 is 8, half 10 is 5. So 8 over 5, you can also say, in your case, 8 over 5. So you can say 8 over 5. Any of these. I don't think they matter. Writing it in exact, to be honest. So there it is. Beauty. That's nice. That's 1.6 or 8 over 5. Next question. So the high jumper was not successful on his first attempt at this height. So he actually wasn't successful in his first attempt. Find the probability. Basically, let's understand. He found the probability that he failed in B. Given that he failed in B, so he failed in his second try, he made it in his third try. Okay, that's what we're trying to find. And we have more work. So given that the high jump has a 0.7 probability of making a successful jump on either the second or third. Oh my god, so much information that's just eating my head in. We have to break it. We have to break this information because it's actually that's a lot. It's too much. That really just confused me a lot. So what I'm going to do is I'm going to take this because I think 100% I'm going to need this to break it apart. So I'm going to put this over here. Let me zoom it in. Okay. So let's think what's happening. So they've given us extra information. It says given that the high jump has a 0.7 probability of making a successful jump on either the second or third try. So basically what they gave us here is the probability that he made it, so probably of he successfully makes it in his second. So second we can say is B, or means union. Third, so the or union, like third is your C, and of course all of them have to be given. He has to fail the first phase, A. Yeah, remember he has to fail your A dash in this case. Yeah, remember for example to make it. You remember if he has to make it B, or second or third, they all have to fail A, because that's how they get into the second and third phase. Yeah? They always have to fail this A. So given that A has to be always failed, basically. And that here is actually equal to that 0.7. Okay. And we're trying to find the probability, yeah. Okay, that could be useful, like using this. So, for example, okay, let's break this apart. We have a union here. But I've already given A dash here just to make it more like that A has to be like, of course, failing. Let's look at this first here. What's probability of B union C? Now that's easy. You use the addition rule. Like for example, if you have the probability of A union B, shouldn't that just equal to the probability of A plus the probability of B minus probability of A intersection B? Now look at this case. This case is different. Now we know our B and C have no intersection. They are mutually exclusive because that doesn't make sense. Think about it. Only one can occur. Like, for C to occur, B has to fail, yeah? They cannot both be successful, you remember? They cannot be both successful. So, there is no intersection. Basically, what we do is that, basically what it's saying is the probability of, union, it's just the single probabilities adding each other up, basically. So, for example, probability of this is basically just, so the probability of B union C, basically you can have B or C. Successful is of course the first thing, yeah? Let's look at actually successfully getting B first. So for example, if you want success to be, first of all, what do you need to in this case have? Well, first of all, you need to actually fail A. Remember, you need to fail A. So you need to fail A, and then you successfully have to make it into B, like that. Which is basically what we just did out. You remember that last working out we did here? Where was it? Oh my god, did I rub it? Yeah. So you remember how we did? We said that the probability of to be successful in B, given that A dash has to be unsuccessful. So look, A has to be. So look, given that A is unsuccessful, we make it into B. Basically, that's what we're doing actually. Which in this case is 0.5. It's that here. Remember? And don't forget now. What about making into C? Now C is a lot of steps, by the way. There's so much. To C, you need to fail multiple steps. Look at that. First of all, you need to fail, of course, A, B, and then make it successful to C, yeah? So we got this phase here, so this phase here, because you need to fail B. Don't worry about this here. This here, remember, it's basically because this 0.4 is, we've already put it in, it's already included in these here. Remember when we did these calculations? So it's actually this, and that, basically. So we want to fail in phase A, so C1. We want to fail in, of course, your first try, fail in the second try, and successfully make it in the third try. So to write that down, how would I write it? I would say the probability of making C, of course, C, given that both A is not made and B is not also made. I'll write it like that. And remember, this here is just 0.7. We just write that 0.7 to make everything simple. So that's 0.7. This here is, remember we already calculated 0.5. It's here. So it's basically making B successful, given that C is unsuccessful. We already did calculations over here too. Here, that's the same thing. So 0.5. Plus, what about this here? Probably that C is successful and A and B are not successful. So what I'm going to do is, this is what we're trying to find basically. This over here, this probably that C given B is basically here. So we're saying C is successful. C is successful. So this is successful. They're given that B is not successful. So basically, this is what we're finding. This is our X. It's that phase there. So how do we calculate it? Well, it's quite obvious. It's just we want both A and B to fail and only C to succeed. It's just 0.5 times X. Yeah? Because remember, this 0.5, it's considering that already this has failed. Remember, these are already together. This 0.5 is already considered that A has failed. So it's just 0.5 times X. This is confusing, yeah. So 0.5 times x. So you multiply those together and you get 0.5x. Yeah, and so x, by the way, x in this case is basically what we're trying to calculate. It's your probability of C given B has failed. So your second try has failed, but C is successful. And we got this algebra here to do. Now, we minus 2, 0.5, we get 0.2, 0.5x. So we get basically x equals 2 over 5. And x is, remember, x is probably that C given B dash. I actually don't know if this is correct. I need to double check it with some of my friends who are tutors, because I'm not sure. This is confusing. I worked through it like this, but I don't know if that's even correct. 2 over 5. So we need to double check, because there's no solutions to these papers. I need to double check with some of my friends here. All right. Let me know otherwise how you would do this. Is that correct? Yeah. Move on. So next question. Question 7. Let f be all reals, so the domain's all reals for this parabola, where b is an element of all reals. Find the values, so there's many values, of b for which the two solutions of f of x have a difference of 5. So when you minus those two solutions. Okay, first of all, how do you find those two solutions? Just use the quadratic formula, of course, because you don't know what the, you can't factorize this, of course. So let's use that. It's really easy. So, of course, it's going to be using the quadratic formula. It's negative b. And our b value is just b, basically. That's good. Plus or negative, b squared. So our b squared is just b squared minus 4. Our a is basically 1. And our c is negative 6. Don't forget over 2a. So 2 and our a value is 1. Okay, beautiful. So we got that. And so your 2x values are going to be, of course, x. So I want to separate them. So negative b minus square root. So b squared 6, 12, 18, 24 plus 24 over 2, and the other one, so x equals negative b plus square root b squared plus 24 over 2. So these are your two solutions, yeah? Your two solutions. And basically we're saying, hey, the difference between them is 5. Now be careful. What do you do? There's two cases, yeah? Like, you can minus this, so you can minus this one, like you can say this one minus this one, or you can say this one minus this one. There's two cases we need to look at, because they're just saying, hey, find the difference. Now, normally in special, you'll use absolute value, but we don't use that in methods, so this is what you have to look at. You have to look at two cases, because there could be different solutions. So what I'm going to do is do this. I'm going to say this here. I'm going to call this solution over here as 1. Let's call this 1. And I'm going to call this solution here as 2. Beautiful. So let's look at the first two cases. Of course, remember, there's two cases in this case. There is, the first case, which is basically, to find the difference is just 1 minus 2. So like 1 minus 2. And that's, of course, equal to 5. That's the difference. And, of course, you got the other phase where it's going to be like the same thing, but these are reversed. So like that's, oopsie. That's there. That's it. See, there's two cases, yeah, we need to look at. Because we don't know what possibilities we can have. So be careful. Look at the two cases to double check. So what's 1? First, let's look at the first case. Like, 1 minus 2 first. So what's 1? 1 is this here, so that solution here. So it'll be minus b squared minus 4ac. So minus 4ac plus 24. What am I doing? 24. And then, well, they both have the same denominator. It doesn't matter. So minus, of course, you want a minus and 2. What's 2? Negative b plus now b squared plus 24 over 2. And you can actually see that if you expand it, these will be a plus here, and there will be a minus here. So it'll be a minus here. And you can see that the b's actually cancel out. This is great. These b's cancel out. And so these two add up, like it'll be negative 2. So these two add up. And don't forget the 2, there's a 2 here. And these two cancel out. Oh my God, this is becoming nice. And you're left out with this here. And this is, remember, the difference is equal to 5. So minus 5, like put that negative into both sides. So it'll be negative 5. Of course, square it. It'll be b squared plus 24 equals 25, and minus 24 on both sides, you get b squared equals 1, and hence b equals plus or negative 1. We got actually two values of b. Okay, be careful with that. So that here, we got two, both like plus or negative 1. Now, we need to also do the same with the here. So let's see, try it this way. So remember, now you're doing 2 minus 1. So again, negative b plus, but because they have the same denominator, it doesn't matter. We can just plus 24 minus negative b minus b squared plus 24 all over 2. Now, of course, this will become plus, and this will also become plus. So plus, and so you can be, the b's also cancel out again. And these two add up nicely. Like these two add up nicely. So, and those two cancels out again. So these two, again, just cancel out because being divided. And of course, that's all equal to 5. Of course, it'll be b squared plus 24 equals 25. And it's the same thing, b equals plus or negative 1. So guess what? It's actually just b plus or negative 1. Both actually cases give you the same answer. So your overall answer, your overall is both these cases. Because remember, there's two solutions. It says find their values. So b is equal to plus or negative 1. Like that. Hope that makes sense. Beautiful. So that's 2 marks there. Next question. Let b be a negative number. So less than 0 means negative number. Explain why the inverse function does not exist when f is restricted from this domain, 0 to infinity. Let's break this down. Okay, so looking at this over here. So remember, for let's do it here. I'm gonna do a lot of writing, explanation here. Try to do some explanation. Can I just space here? Yeah, there isn't, but who cares? So let's write f of x here. Let's just write f of x, and let's just explain, and I'll delete this. Just so here's gonna be an explanation and how I want you to approach to think about it. So visually. So we have x squared here, so it'll be x squared plus bx plus, sorry, it was minus 6. Minus 6, yeah? Yeah, it is. Okay, so they're saying that b is a negative number. What does that do, though? We need to look at it. So first of all, how do we want, so for our inverse function to exist first, for our inverse function to exist, it has to be a one-to-one function. And for it to be a one-to-one function, it must basically pass the horizontal line test. So if you have a quadratic, for example, like this is not a one-to-one function, because if you draw horizontal lines like that, can you say that intersecting the graph twice at every point? If it does that, it doesn't pass it. Remember, it only has to intersect it once. So for example, if you had a graph like this, so now if you draw the horizontal line test, look, can you see how they intersect only at one point? Now it passes the horizontal line test. So what we need to do is this. This quadratic, in this case, kind of think of it like this. Let's look at where this turning point is. It's important because most of the time, it's that turning point that's a problem. So you can have you see how when we draw a quadratic, yeah? This turning point creates the biggest problem, because that's where you start to have, when you draw a horizontal line test, you get two solutions. But if you don't have a turning point, like that turning point, something like that, if the turning point's there and there's no other side, when you draw the horizontal line test, it passes. So first of all, we need to look at the turning point of this. Remember, to find the x value for a turning point, it's really easy. So remember, you can just use this quick formula, negative b over 2a. Remember that formula? That's the x value for your turning point. So it's going to be negative b in this case. Our a value is just 1, basically. It's just negative b over 2. Think about it. Wait. If b is a negative number, yeah? If b is a negative number and it's being multiplied by a negative number, now it's a positive number and it's being divided by 2, basically this here is an overall positive number. We can say that hence, like this number here is greater than 0. It's a positive number. It means that your turning point, the x value for your turning point is a positive number. So I'm just going to make up one. It will look like this, basically. You see, like, for example, this here. You can see how this turning point has a positive x value. It's that, basically, yeah? But this is for the whole cases. Like, think about it. It's for the whole thing, yeah? Yeah, so our turning point's always going to be positive. Okay. But then you look at it, you're saying, hey, explain why the inverse function does not exist when f is restricted. So this function is only restricted from 0 to infinity. So imagine, like, from here, let's rub this out. Like that, like that. So you know how that's now restricted to 0 to infinity? Look how big problem. This is not a one-to-one function. You can straight away realize, because it doesn't pass the horizontal line test. Why? Because there's actually a turning point, a minimum turning point, yeah? There's actually a minimum turning point from 0 to infinity, yeah? Where, because your turning point, your x value for your turning point is greater than 0, because, yeah, it's always greater than 0. So there's always going to be a turning point. as much as you want to play with it, it's always going to be a turning point. Yeah. So for example, if the more b value becomes like, it's always negative. So yeah, b values, yeah, you're going to have a turning point always greater than 0 in this domain. So basically it's never going to be an inverse function because it's always going to have this turning point and it's going to fail this one-to-one function. The way you kind of, I would explain it basically, it's really hard to explain. I hate these worded questions where you do have to explain. Now what I'm going to do is do this. So I'm going to actually just put this graph over here. It's because it's a really good example to break the question down. And really, let's explain it. This is how I would explain it. I know it might be, I hate explaining these questions. It's just a little bit, like I want it first visually, but writing is such a problem for these questions. So I'm going to give you my explanation, but maybe, yeah, it's not the best. But for example, what I'm going to say is, you remember how your turning point, yeah, is negative b over 2, yeah? Now we know, we said as b is a negative number, as b is less than 0, so a negative number, we learned that this whole thing, negative b over 2, is greater than 0. It's a positive number. It means it's always going to the right, yeah? Now, let's think about it. So if this is your turning point over here, so remember this is a negative b over 2. If you look at the left side of it, so like, x is less than negative b over 2. So in the negative part, we can see that the function is decreasing. It's going down. So we can say that, because we're I think trying to prove that there is a minimum turning point in that domain will tell us, we can prove that, then it's going to fail. I think that's how I would approach it. So we can say that, as x is less than that x value for the turning point, so x is less than negative b over 2a, so in that left hand, we know that f of x is, because it's a minimum turn, is going to be decreasing. F of x is it, would you say decreasing? Like, decreasing, yeah. I'm going to say strictly decreasing, but yeah, decreasing. And when x is basically like equal to b over 2, it's a minimum. We know it's a minimum because your parabola is always x squared, so it's always, where is it? So it's always a positive x squared, so it's a minimum turning point. Minimum turning point. And when x is greater than sorry, I'm supposed to put a negative there. Negative b over 2a. We know that f of x, as you can see, when you go above it, so we can see after that, it's increasing. F of x is increasing. And these all are within the domain. These are all within x, your actual domain, 0 to infinity. Like we said, 0 to infinity, this domain. This proves that there's like a minimum turning point, as from the graph, yeah? You can see that in this graph. Hence, you can straight away say that, like, hence, it fails. The horizontal line test, of course, it will fail the horizontal because there's a turning point. Horizontal line test. Test. As it's not a 1-to-1. Hence, F inverse does not exist. This one's a little bit, I hate these ones when they start putting some rubbish like this. It's one where the inverse function does not exist. It's only 1 mark, but yeah, it's such a pain to think about it. Like you can easily understand how it works. Yeah, we kind of visually understand that it's 100%. The inverse doesn't exist, as we saw from the graph, for any b values that's less than 0. But explaining it, writing is the hardest part. In how can you interpret that to put it is always one of the hardest part. But they tend to be always 1 mark, so it wouldn't be a two of fuss, I would say. But yeah, that's how I would say it. Maybe it could be wrong, maybe it could be right. Any way better? Probably there is better ways to write it, but I would write it like this. I'm not even, yeah. Let's try to do the next question. Okay, we're back to the algebra. Oh, forget about that rubbish grammar. Yuck. Find a rule for the inverse function of f when f is restricted to this domain, negative infinity to 0. Beautiful. Let's do this. So this is just, again, going back to the original. So remember, to find the inverse, you need to first let f of x equal y, and you want to swap x and y. You always have to do this step, yeah? Don't forget this step. So what we have to do in this case is, I fully forgot what f of x was, actually. Let me write that down, because I'm going to forget it again, so I might as well. So x squared, what's it? Plus bx minus 6. All right, beauty. So first of all, okay, let's swap x and y. So that's will be y now. So that'll be our x, of course. This will be our y, so that'll be r squared plus by minus 6. And we want to solve for y. Now, this is a quadratic, as you can straight away see. So I'm going to minus 6 on both sides. Minus x, sorry. To bring that x to the other side equals 0. And I'm going to look y squared, because I'm solving for y. It looks like a quadratic. So plus negative 6. I'm going to put these together. Equals 0. You see that? So like, for example, this is my a. This is my b. This is my c. You know, for a quadratic, a squared plus b squared equals c squared. What am I... Did I just say the Pythagoras theorem? No. Like, ax squared plus bx plus c. That's basically... I just said Pythagoras theorem in my head. I don't know what just happened to me. So yeah, we got that. So we're going to use, of course, quadratic formula. So it'll be y equals... remember, quadratic, it's going to be negative b. So negative b, that's our b value, of course. Negative b plus or negative b squared. So it'll be just basically b squared in this case. Minus 4. Our a is, of course, 1. Yep. And our c is negative 6 minus x. Over, don't forget, 2a. Now, a is just 1, so just 2. Okay, so a little bit simplifying this much further. So negative b plus a negative. And we need to look at, okay, b squared. So that'll be 6, 12, 18, 24. So it'll be plus 24 plus 4x all over 2. Now, we need to double check which one is it. Is it the plus or negative? Now, what I like to do here is I'll split it up, actually. Splitting it up will make it so much easier. So let's split it up. Negative b over 2 plus or negative b squared plus 24 plus 4x over 2. Okay, like that. Now, think about it. We said that... Is this... Wait. Yeah, it's still for... Like, if you can see, it's still for b is less than 0, by the way. So it's still negative. So if b is still, less than 0, remember this here, it's going to be always positive. Remember, like, it's like the same as the other, our turning point. So this here is always positive, this here. Yeah? Now, our goal is to... Okay, first of all, like, this is our equation now, yeah? This is our equation for the inverse, yeah? Now, remember that the range of our index is just the same as the domain of the original. So this is the domain of original. So our range of our inverse now, of our inverse, is just going to be the same as this domain of the original. So basically, like, the y values that we're going to have are always going to be negative, as we can see. So for example, if this is positive, yeah, should we take the positive or the negative? Like, think about it. So this here, of course, this has to be positive because it's a square root. This is going to be always positive. So of course you want to take the negative, because like, if you have a positive and this is all, if you put positive here, plus, if you put a plus and this is always positive because you've got the square root here, positive plus positive is just positive. And we don't want that. We want to make sure that we have negative values. So of course the best case is to put the negative here, making sure we have the negative in here, this negative. So if we put that negative there, if we put that negative here, where of course this is always positive, this part, at least positive minus positive, there's going to be some negative values in there. And so, of course, we want to take that negative. So that's how I would approach that question. So, of course, rub this rubbish out, that positive, and it's actually the negative. I'm going to kind of take that out. And don't forget to write the original equation. So it's now going to be f inverse of x equals negative b minus b squared plus 24 plus 4x all over 2. Wow, that was a pain, I'm not gonna lie. So it's perfect. Let me just highlight that. Okay, that's it. So let's move on to the next question. Next question. Let g be a function with a maximal domain of this. So this is a normal normal log. So find the value of b. So there's only one value. So find the value of b for which the maximal domain of this composite function, so g of f is this. Okay, doesn't seem too bad. So let's break it apart, because just by looking at it gives you a headache. So we need to break it apart. Okay, so we're saying g of f. So basically g of f of x. Now we know for a composite function to exist, what do we know? We know that the range of the inner function must be a subset of the domain of the outer function. Isn't that correct? Now, also they've given us that the domain, like where it exists, this composite function, the maximal domain of it is, negative 2 to 2. Now, think about it. We now know, they've also given us that the domain of this g of f, your composite function. Now, if you don't know, the domain of your composite function is it's the same as the domain of the inner function. And our inner function is, of course, f in this case, yeah? So it's equal to the domain of the inner function, and which is, of course, in this case, it's negative 2 to 2. So guess what? We actually have the domain of f. This is a beautiful actual case because we've actually now, we have the domain of f. This is great. And we also need to look at, we can actually even find the range of f. If you think about it, we can actually also find the range by, look at this. So what's first the domain of g? The domain of g is, by the way, this is just a log, and to find the domain is just to make the inside here to be greater than 0. That's how you can easily solve it, find the domain, so make it greater than 0, because remember, inside a log, it's always positive and not equal to 0. So bring that 2 to the other side, and divide both sides by -1. So if you do that, remember, dividing by negative, if you divide by a negative number, it flips the sign, it'll be -2. You're basically saying your domain is from -infinity to -2, non-inclusive. So your range has to fit in with this. So for the composite function to exist. So I'm just going to rewrite it as the same. So like this. So the range of f must be like, this is an example, but it just has to lie within this range. So it might not even be this, but we're actually, I mean, we might as well, yeah. So it might, like, it's not going to be that, but like it's something that fits into that. So if I like to, let's draw a number line, maybe that will help out. So for example, -2, let's say -2 is here. Open circle all the way there. So we can only have values, the range of f has to be within here, like within this here, somewhere around there. So yeah, so what I'm going to do is, now we've actually got so much information. We actually have the domain of f, so we might as well draw f. Yeah, because remember, f is that rubbish function, that quadratic. So I'm just going to draw it. Okay, quadratic right here. And let's draw it with this domain. So remember, it's a quadratic. I don't know how the quadratic looks like. Let's say it looks like something like that. Where, remember, these domain here, this is an open circle. Right, let's make it, I want to make it symmetrical, actually. Let's make it symmetrical like this first. Remember, it might not even look like this, but look, we're going to see how it works. So like that. Sorry, these are open circles now. Because remember, that's -2, and that's 3. That's your domain. That's perfect. Look, the domain works. But does the range work? Remember, coming back here, we need to, remember the range? We might as well just put it as the same as the range of this, so it can be a subset, by the way. So the range of this must also be like, the range of our f, you know this function, the red one, has to be from -infinity, so it has to be below to -2. Damn, as you can see, this is rubbish. Like, it actually be translated down, basically. It has to be like, look, it has to be translated down like until here, somewhere around here, yeah? Because look now, so imagine this here is -2, yeah? Can you see how the range is like some value? It's not -infinity, but it still fits in, yeah? So imagine it's like -4, yeah? Can you see how, imagine that's -4? -4. So it's an open circle, -4, all the way to -2, like there. See, it personally fits in with that, what do you call it? The subset of it. So it actually exists. So this is what it looks like. This is a typical, you would say, of how it looks. So beautiful. And this is how the graph would look like. Not like, yeah. So we use this here. We can use this to actually find b, because, for example, we know that, for example, you can sub in for f of x. Yeah, this is our f of x. If you sub in 2, it should output -2. Or when you sub in -2, it should output -2. Does that make sense? Because look, -2, when you sub it in, it should give us -2. All right, so let's see if, oh, what's just happened there? Come on. Yeah, I don't know what just happened here. Let's do it. So what I'm gonna do is, let's do it. So, for example, if I sub in -2, so if I sub in this -2, the y value has to be -2 for this to work. Or the other case where if you can sub in like f of 2 and it also equals -2. And remember, f of x is what? F of x is that. Still remember it now because it's in my mind how long we've been using that equation. So remember, f of x is what? X squared plus bx minus 6 now. So it means the y value is -2, x squared. So -2 squared is positive 4. -2b minus 6. Is that correct? So that'll be 4. So bring that negative 6 to the other side. It'll be 6. So yeah, 4 equals 4 minus 2b, which is 0 equals -2b, and hence b equals 0. So we got b equals 0 for the first case. Let's try the other case. We need to double check the other case. So if I just submit that, so it'll be 2 squared, which is 4, plus 2b minus 6 equals negative 2. So negative 2 minus 2b equals negative 2. As you can see, both sides have negative 2, so it'll be negative 2b equals 0. Cancel. And b equals 0. Okay, both have b equals 0. So the only answer, and it says find a value. So that's the only value. B as your final answer is b equals 0. That is really tiring. Wow. I'm already kind of feeling drained. This paper really feels like really long. Okay, that's that one. Okay, let's do now question 8. So you have f of x, which is, from 0 to infinity, when this is your f of x, where k is a positive real number. Now, consider the particular case where k is equal to 6. Show that the derivative of this is equal to that. This is nice. So, because basically we're just deriving this, which you just have to use the product rule, because there's two functions being multiplied by each other. So, for example, you have u here, and this is your v. So, what we can do is, of course, write product rule. I'm just going to explain this. So we're using the product now. Rule. Okay. Let's use the product rule here. So for this product rule, remember you let u, so this is going to be our u in this case. So I'm going to be our u, which is x, and our v is going to be this here. X plus 6. U dash, when you derive u, it'll be 1. V dash. How do you derive when you have a square root function? Remember, so there's actually a quick trick. If you want to derive anything with square root, like normally the typical thing you will do is like if you have x plus 6, the same as if you want to derive this, you will have to make it, this whole thing to the power of half. It's just too long. Don't do that. There's a quick trick. If you want to derive, basically, ddx, if you want to derive anything with a square root, so let's say you have square root and you have a function inside of it, make sure to memorize this. This is such a lifesaver. It's just f dash of x over 2 root, so 2 root f of x. For example, if we wanted to derive this is your f of x. This is the function inside here. It's just, so if I want to derive this, it'll be deriving the inside here, which is just 1, over 2 root f of x. You know how f of x is x plus 6? I'm going to write x plus 6. How easy was that? In 1 second, I derived it. Look how nice. So I can write that there. 1 over 2 square root x plus 6. Easy. Okay, so make sure you know that rule. It's so beneficial. Okay, beautiful. So what I'm going to do is I'm going to have to, of course, what the product rule is. This is how the product rule works. So dy dx is, so to find the product rule, remember it's u times v dash. So it's basically like u times v dash, because I'm proving here, plus v times u dash. Yeah, so v times u dash. So let's do that there here. So, for example, in this case, it's u times v dash, which is just basically x over 2 square root x plus, and then you multiply these two, which is square root x plus 6. And that is it. That's your derivative, which, now, to write it nicely, you just rewrite this whole thing, yeah, like, so look, the derivative is equal to that. Done. So I would write it nicely now, like ddx of x square root x plus 6 is equal to this here. Done. Beautiful. That's a nice, really nice question. Just using a basic product rule here. Nice. Next question. Hence, so using that, or otherwise, evaluate this integral from 0 to 6 f of x. So f of x is this, but it's subbing 6 basically in. So if I subbed in 6 here, it's just the same as that. So this is actually just integration by recognition. So what I'm going to do is I'm going to rewrite this here. Let's rewrite it, copy and paste it just over here. So I'm going to show you how to integrate this. ddx, this is just an integration by recognition equation. So ddx is x square root x plus 6 is equal, let me write that nicely, this one, square root x plus x over 2 root x plus 6. Now look at this. Our f of x in this case is this over here, isn't it? Yeah, because imagine that's f of x, but of course when k equals 6 in this case, so look, it's that over here. So what I can do is I can just, this here is just f of x, so I can just rewrite it as f of x. just take it off and write it as f of x. Just make my life easier. And what I can do is rearrange this whole equation to make f of x the subject, and I can sub it into this integral. For example, I'm gonna so f of x, I'm gonna bring that to the other side. No, bring this to the other side actually. So f of x will be d dx x square root x plus 6 minus the square root, close the bracket. Of course, you want to close that bracket. Then minus the square root of x plus 6. That's it. So that is your f of x basically function. So if we wanted to find the integral of it, of f of x, from of course 0 to 6 dx, is basically finding the integral of 0 to 6 of this whole function. I can just copy and paste it right over here. There. Dx. Beautiful. So now we can actually integrate this. So it's so much easier to integrate. So if we integrate this, look, an integral and a derivative cancel each other out. So it's basically, if you want to integrate this, it's just the same as this. Beautiful. That's how integration by recognition works. And don't forget, how do you integrate this over here? So let's do it here. So it's basically, how would you integrate this? Well, first of all, you want to basically make it a index, so like half. And this is how, you remember, so it'll be -1 over, you derive the inside, which is just 1, and you plus power of 1 here, so it'll be 3/2. And you rewrite the whole thing to the new power, which is 3/2. So it'll be -2/3 x. So this is in your formula sheet, by the way. Power rule for integration. So it's basically writing this. It's negative. Oh my, I feel drained. I'm not gonna lie. So x plus 6, 3/2, and close that down. That's it. So that's how you integrate that. From where? From 0 to 6. Okay. So we're nearly done. So now we just sub in the values. So we need to sub in 6 first. So 6 plus 6 is 12. Minus 2/3. 6 plus 6 is 12. 3/2. Minus, so if you sum in 0, this whole thing will be 0. So it'll be minus 2/3. So if you sum in 0, it'll be 6. 3/2. Close the bracket and close it. Let's simplify this, because you can actually simplify 6√12, yeah? We can write it as, so root 12 is what? You can write it as 2, so 4, 8, 12. So 2√3, so 2√3. Don't forget, there's a 6 in front of it, so it'll be 12√3. So this will be 12√3. Nice. So let's do the next part. For example, here we have 12 to the power of 3/2. So what we can do is we can write it as the square root of 12 to the power of 3. The square root of 12, we did do it. We was 2√3. And remember, your to the power of 3. So 2 to the power of 3 is 8. And the square root of 3 to the power of 3 is basically 3 times root 3, which is 8, 16, 24, 24√3. And remember, you're multiplying also by like -2/3. So like multiply by -2/3, which this goes into 8 times, so 8, 16. So it'll be -16/√3, like times root 3 basically. That's a lot. Oh my god, -16√3. Okay, we're making a lot of progress. So I like to do the algebra on the side to just make my life easier, make it not ugly. So for example, these two kind of cancel each other, these plus or negatives, so it just becomes plus here. Same with this, so doing the same thing. So you can write it as like 6 to the power of 3, and then take the square root. Which you can write it like basically 36 times 6, because like, you know how you can write it as 6 times 6 times 6, that's 36. You can write it like that. And like the square root of 36 is just 6, square root of 6 like that. Oh my god, yep, we got that. And then don't forget, timesing it by 2/3 here. It's 2/3 here. So this 3 goes into it twice, so it'll be 4√6. 4√6. Okay, we're making kind of, we're nearly done. Okay, which equals, of course, these two kind of minus each other, so it'll be -4√3 plus 4√6. Hence, your final answer is, I'll make it nicer actually. Take a 4 as a common factor. Say √6 minus √3 as the final answer. That took so long. Wow. But it wasn't too bad. It was not bad. So like, it was really alright. But yeah, it just feels drained. I feel like it's a draining exam. Last question, yes, this is the last question. I'm really happy to get this paper done. I'm actually. So find 0 to k f of x dx in this form. So it's kind of the same thing, okay, where a and b are integers. Now, what I'm going to do is actually not bad. So it's it's like the same thing, but now it's 6. You know that 6 now it's just back to k. So what we can do is like everything's quite the same. Like what you can just do is do this. You could just recopy this whole thing here. You know, just recopy this whole statement. Just duplicate it, bring it over here. And you know this is like, you know how this is 6 here? Replace them with the k's. So this is k. This is a k. And this is a k, yeah? See how easy that is? Because that's how you do this one. And it's only 2 marks because this is the top one's most likely to help you. That's what it's doing here. And it's more even simplified because what you can do is like this can all be simplified. We already simplified most of it. Coming back here to this, like we can actually just copy this here when it's fully simplified. This part here, duplicate it more again, and so when this integrates, it's equal to this. Now, of course, remember take these out. These 6's here. These are going to be, of course, k's. Just double checking, and this also is k, by the way. Just double check them. 2, 3. Yeah, nah, they're all the same. They're all the same. Yep, they're all the same. There's nothing really crazy. Shouldn't be a problem with that one. Okay, perfect. Done. So now I'm going to do the algebra now. Look how much easier, because you're just using the other one and just replacing those k's with those 6's with k's. Let's do this one. So remember, you sum in k first. So k be root 2k here. Minus 2 over 3. K plus k is just 2k. 3 over 2. Minus, and then you sum in 0, that'll be 0. This will be negative 2 over 3. Which is basically k to the power of 3 over 2. Done. Close it. Which is, in this case, like k root 2k. So, okay, first of all, like this here, how would you write that? So it's 2k. You can write it to the power of 3 and then take the square root. You have to get rid of that 3 over 2, which is basically ak to the power of 3 square root. Like, think about it. You can write this as just like 4k squared times 2k. Square root, yeah? It's the same as ak, so it'll be 2k square root 2k. 2k square root 2k, yeah. So you can write this, yep. And then you're multiplying it by negative 2 over 3. Negative 2 over 3, which is negative 4k, 2k over 3. Negative 4k, 2k over 3. Okay. And then that's going to be plus 2 over 3, k, 3 over 2. And let's also simplify that, like what we were doing. So just simplifying it like this on the side just makes everything easier. The algebra just simplifies slowly. So you can write that k to the power 3, take the square root. So you can write that as just k squared times k, the square root, and k squared is just k. You can write it like that. And then don't forget it's being multiplied by 2 over 3. So it'll be like that. So we can replace this here. 2k root k over 3. Alright, so I'm going to make them all as a common factor, like the common denominator, sorry. So multiply everything by 3, so it'll be 3k, 2k, plus 4k, sorry, not plus 4k, it's minus, there's a minus 4k, 2k, okay, plus 2k root k over 3. So it'll be negative k root 2k plus 2k root k over 3, simplifying it. And they want it in the form of k root k. So this one's k root k. We need to get, like, this one's 2k, so we need to get rid of that root 2. So we can write that as negative k. So we can write that as like negative root 2, basically times k root k, like that. Yep. Plus 2 k root k over 3, like that. Beautiful. And then, yeah, so then what we want it to be is we want like k root k, so it'll be 2 minus root 2, don't forget, over 3, and don't forget k, so like k times root k. K times root k. There it's the same thing, like that. So you got, look, a is 2, and then root a is 2 again, b is 3. Perfect, that works. That's the answer. That actually looks perfect. That one looks nice, so I hope that's correct. Beautiful. Look, I'm be honest with you. What an absolute paper that's rubbish. I don't know, for a reason it was so draining. It's a really, there's some questions that I just, like the probability one, I'm still confused though. Like, I'm not gonna lie with this one. This one's a little bit ate my head in. Like, I fully understood a little bit of it. Like, I understood how to work through it, but it was just like, how are students gonna, like, if they're in a stressful mode, how the hell are they gonna do this one? I'm not gonna lie. That was a little bit questionable. The papers, like, these ones were alright. Again, this one's hard, so I would have expected this to be the last question, maybe. There was a lot of hard questions in the middle. Like, there is some explanation. I don't like the explanation, but yeah, this paper's, like, quite, I would say, yeah, it was hard. I wouldn't, I would have, yeah, when people were saying it was hard, I do agree with them. There's so much rubbish in there. Yeah, so, but don't worry, guys, you've done it, so just be happy, like, you're all done with it. At least it's in the bin, throw it in the bin, it's all good. Those who've done overhands, yeah, forget about it, you're lucky, now you're free, so just, yeah, be happy now. But yeah, what an absolute rubbish paper. I hope you guys enjoyed this, video, and hopefully it explains so much and helps you with your studies, yeah? Good luck, everyone, and bye-bye!